Alright, we are going to finish this chapter talking about functional groups. So, carbon and hydrogen are not the only elements that can be present in organic compounds. There are certain groupings of atoms that show up over and over again in nature. These groups of atoms often have very specific properties in reactivities. And so because they have these very specific properties, and because they show up all over the place, we have given them a special name. We call them functional groups. And each one of these things will also have its own special name and properties that go along with it. So here we have just the 7 most common ones. There are more than this, but these are by far the most common functional groups that you're going to come across. There are some other ones, like there's some sulfur groups and things like that, but those aren't as common. These 7 are by far the most common ones that you'll see wherever you look in organic chemistry. So we have alcohols. This is where we have an OH group attached to a carbon. So as you can see here, there are R's all over the place here. R just represents, I like to think of it as random carbon stuff. It's just the molecule continues from here. So we don't actually care what else is in the molecule. The R here is just representing there's more carbon. The carbon keeps going. So it could be a carbon that's single bonded to something, a carbon that is double bonded to something else. We don't care. Just the molecule keeps going. That's what the R is representing. So there is not an element R. The R here is just random carbon stuff. So we have an OH group attached to the carbon. This is an alcohol. So ethanol is an example of this. It's a booze, ethyl alcohol. Ethers are another functional group. This is when we have an oxygen that is bonded to 2 different carbons. And so this is what we call an ether linkage or an ether bond. So ether groups have an oxygen bonded to 2 other carbons. Aldehydes are where we have a carbon that is double bonded to an oxygen, single bonded to a hydrogen, and then is connected to the rest of the molecule here. So aldehydes are at the end of the molecule, essentially. The molecule doesn't continue on past an aldehyde. And this was true for an alcohol as well. The molecule doesn't continue on past the alcohol. But aldehydes here are the end of a molecule. Ketones, on the other hand, still have the carbon-oxygen double bond, just like the aldehyde, but now instead of also being attached to a hydrogen, in a ketone, the molecule keeps going past that, so there's more carbon in both directions attached to the ketone. So the ketone is going to be in the middle of a molecule and have that double bond between the carbon and the oxygen. A carboxylic acid is very similar to the previous 2, and if you notice here, really all 4 of these are related to one another. A carboxylic acid has that carbon-oxygen double bond, just like the previous 2. Only now the other thing that the carbon is attached to, other than the rest of the carbon molecule, is an OH group. So this is essentially a mixture of a ketone and an alcohol that gives you a carboxylic acid. And this is an acidic group. Molecules that have this group in it will be acidic. They will have acidic behaviors, like acetic acid, by the way, which is vinegar. Vinegar is actually a carboxylic acid. So if we have carbon double bonded to oxygen and then bonded to an OH group, that is a carboxylic acid. If, on the other hand, we still once again have that carbon-oxygen double bond, that's the thing that kind of holds these 4 similar to each other, but instead of being bonded to the rest of the carbon or being bonded to an OH group, in an ester, we have an ether linkage. So this one is kind of like a combination of a ketone and an ether. So we have the double bond here, and this carbon is bonded to an oxygen, which is bonded to another carbon. So methyl acetate is an example of that. So we have the carbon double bonded to an oxygen and single bonded to an oxygen, which is single bonded to another oxygen. So then the last type of functional group here is an amine. And this is the easiest one to identify just because it's, is there a nitrogen? If yes, it's an amine. We don't care how it's bonded to stuff. So here it shows that bonded to 3 other carbon things. It doesn't have to be. It could be. Just as long as there's a nitrogen, it's fine. So like in the example here, it's not bonded to 3 carbons, it's bonded to 1, and then there's hydrogens attached to it as well. That's still an amine. As long as there is a nitrogen present, it is an amine. Alright, so these are the 7 most common functional groups that you'll see in organic chemistry. I want you to be able to identify these. So if I give you a Lewis structure, or something similar to a Lewis structure, something like this. This isn't strictly speaking a Lewis structure because you're not showing the lone pairs and you're not showing the individual bonds between the hydrogen and the carbons. But if I give you something like this, I would expect you to be able to recognize, oh, look at that, it's a ketone. Or look at that, it's a carboxylic acid. So you should be able to identify what groups are present in different molecules. And by the way, if the molecule is large enough, it's possible to have more than one group. That's actually very common. In really small molecules, it's just because the space is limited. It's not the easiest thing to have more than one. But in larger molecules, it is very, very common to have multiple functional groups in the same molecule. Just real briefly, I want to talk about some of the properties of these different functional groups. This slide is pretty much just reiterating what we just talked about a minute ago, and that there are more functional groups that we've seen here, but these are the most common ones. So alcohols, these tend to be flammable, and actually most of the functional groups we're going to look at here, most organic molecules in general tend to be flammable, but alcohols especially tend to be flammable. Some of them are actually quite toxic, so like methanol and isopropyl alcohol. You should not be ingesting those. You will really hurt yourself. It's kind of hard to really say that they have certain properties other than that, just because they're so pervasive. They're everywhere. There's alcohol groups all over the place. So it's kind of hard to say that they have a certain property or some other certain property. They're everywhere. One thing that alcohols do kind of have in common is that they do tend to, if you have quite a few alcohol groups especially, they do make things dissolve in water very easily. Ethers, on the other hand, these are very common solvents for organic reactions because they tend to be mostly non-polar with a little bit of polar nature, and so they tend to be pretty good solvents because of that. They also boil at very low temperatures, and they are extremely flammable. So if you think alcohols like ethanol are flammable, you ain't seen nothing yet. Ethers are crazy flammable to the point of being explosive. Crystallized ethers are actually used as explosives in some situations where you take an ether molecule that is normally going to be in solution, usually dissolved in water or some other solvent. If you take that and you form solid ether from it, that is very dangerous. Ethers throughout the history have actually been used as anesthetics to knock people out before surgeries. This was back before we had good anesthetics, because the ethers actually do damage the nervous system. Now, back in that day, have your surgery awake and aware of what's going on, or risk some slight nervous system damage. Most people would pick the risk damaging your nervous system a little bit versus having surgery done on you while you're awake and aware of what's happening. But we have much, much, much better options now. Aldehydes and ketones are very... this is another example where it's kind of hard to say they have one specific kind of property because they exist in lots of different molecules, and depending on what else is in the molecule, they can have very different properties. There's lots of molecules that you're familiar with, either familiar with the name or have interacted with them a lot, that are aldehydes and ketones. So for example, cinnamon aldehyde and vanillin. The names there are not lies. This is actually the molecules that give cinnamon and vanilla their smells, I believe. I know the vanillin, that's what gives vanilla its smell. And I believe cinnamon is the same thing. I don't think this is the taste molecule. I think this is what gives the molecule its smell. And perhaps the taste as well, but I believe it is just the molecule that gives cinnamon its smell. Benzaldehyde is another one that you might have heard of. That is an aldehyde. Nail polish remover is actually a ketone molecule. So they have lots of different kinds of chemistries, lots of different molecules that contain aldehydes and ketones. It's kind of hard to pin down a specific kind of chemistry because of that. Carboxylic acids, on the other hand, do have specific chemistries, and the chemistry is an acid chemistry, as the name implies. So these tend to give you molecules that are sour or bitter to the taste, and you do drink and eat carboxylic acids all the time, because things like citric acid have actually 3 different citric acid or carboxylic acid groups in it. Carboxylic acids are not the strongest acids usually, so some of them are safe to ingest, like citric acid. Other ones not so much. So don't just go out there and say, it's just a carboxylic acid, no worries. Like vinegar, which is a carboxylic acid, if it's concentrated enough, can kill you. It's really nasty if it's really concentrated. But there's other situations where it's not quite so bad. Esters, on the other hand, not going to give you acid chemistry with those. Instead, esters are known for very strong smells. Like I've said, most organic chemistry, most organic compounds have smells. Esters take it to a whole new level. Esters usually have very strong smells. Most of the things like perfumes and colognes and things, if it is a carbon-based molecule, which it usually is, the place they get their smells from are esters. So like the smell of an apple, that is an ester compound that gives it that smell. So esters tend to have very strong, very pungent smells, sometimes for good and sometimes for bad. On the other hand, amines, so these are carbon compounds that have nitrogen in them, they tend to be very reactive, but what we tend to know them most for is they're very, very strong and, as far as I'm aware, always bad smell. These have very, very strong, very nasty smells. If you've ever smelled a dead animal before, you were smelling amines. You were smelling carbon-based compounds with nitrogen in them. So there's a compound called cadaverine and putrescine that are amine organic compounds. And as the name implies, the smell of this thing is putrid. That is the smell of decaying flesh is what you smell there as these amine compounds. So these tend to have very, very nasty smells, and they also tend to be fairly reactive, partially because of the lone pair on that nitrogen in the molecules. It allows it to participate in reactions that it wouldn't otherwise. Alright, so the last little thing here, just real quickly, I want to mention polymers. These are very, very, very large molecules with where you can have literally thousands, if not millions, of carbons in a molecule. And actually, that's actually lowballing it a bit. There are actually some polymer molecules where you have carbons linked together. So if the line that I'm drawing here is a bunch of carbons attached to each other, like several hundred carbons attached to each other, you can have linkages where through those linkages you can literally have trillions, and I do mean that literally, trillions upon trillions of carbons that through linkages are all connected together. There are some car bumpers out there that are made of certain kinds of plastic where the entire bumper is one molecule because of the interlinking of the carbons. So these are giant molecules. And because the molecules are so large and often have that very strong linkage between chains of carbons, you can get relatively strong yet flexible plastics. And so there are lots of different kinds of polymers. I'm not going to have you identifying all these different kinds of polymers. I just wanted to make you aware that they existed and what the chemical structure of the polymers that you use in your everyday life look like. So you probably recognize some of these, like polystyrene or polypropylene. So if you look at the, this is PS, PP, if you look at the, and this is PE. If you look at the symbols on the plastic, they often have these letters. So this is PVC, which is what they make pipes out of, PVC. So there's lots of different kinds of these polymers, and the groups attached to the backbone, to the chain there, is what gives them their unique properties. Alright, so this is just, again, kind of talking about the same thing there, where you can have giant pieces of polymer like these here. That most likely is a single molecule, which is just kind of crazy to think about. Alright, that'll be it for this chapter. We're going to start the last chapter, biochemistry, in the next video. So I'll see you over there.